Okay, so we have question you see here. You want to plot this, and I said, always when you have a polynomial, you're going to automatically find the x and y intercepts and plot them. Okay, so okay, so now you really want to write out a little bit about what you're doing and why you're doing it, because if you do, you'll be much more likely to remember to do it correctly when you're tested on it or when you need it in a subsequent course. Okay, so I keep emphasizing that it doesn't take long to write a few sentences down. But of course, in class, sometimes you just jump to the case. You really, when you do the homework, you really ought to be writing these out, writing out what you're doing, because you learn it much faster that way. Even though it takes a little longer to do the homework, 3 weeks down the road, you're going to remember it much better, and you won't have to go back and relearn it. Okay, anyhow, so the x-intercept, y equals 0. So, of course, this is y equals p of x. We're going to assume it's a y versus x. And we're going to get 0 equals x minus 5 times x plus 4 times x plus 6. Now we're going to separate this out into 3 equations. X minus 5 equals 0. X plus 4 equals 0. And x plus 6 equals 0. And you really ought to write it out that way, because when you get some ugly looking thing here, it has all kinds of expressions in these parentheses. You're going to want to know that, well, we separate it out. We can't just do it by looking at it. Okay? We separate it out into equations and we solve the equations. Well, the equations are really easy to solve. It's just one step in each case. There it is. And then we check our solutions. Okay, well, you can do that in your head. You know, plug in 5, you're going to get 0. Plug in -4, you're going to get 0. Plug in -6, you're going to get 0. And you already know that. And you really can just, in this case, just look at it and see what you have to do. Still a good idea to write it out at least a dozen times on each type of a problem. Okay, so you retain it better. Okay, well, the x-intercept, I'm not writing down all the details. I probably want to put the substitution step: 0 minus 5, 0 plus 4, 0 plus 6. So there's a step I've skipped that you really ought to include, just again to reinforce it. And that equals -120. And now we can sketch a graph. Let's see, we've got -6 over here. And then -4 will be 2/3 of the way from 0 to -6. And 5 will be out here. It'll be here. And then the y-intercept -0, -120. Okay, so it's even a good idea to list the intercepts. -0, -6, and list them right, like I don't half the time. I'm just focused on the fact that x equals, y equals 0 for the x-intercepts. And so we have -6, 0, -4, 0, 5, 0, and 0, -120. Well, there they are. Well, now we've got to draw a smooth curve through these points. You can't go through the x-axis except here, here, and here. So if you try to draw the curve starting from up here, you're going to come down through this point and go up through this point, and you're not going to be able to get back to this point, right? So you can't start up here. Again, if you start up here, you just can't do it. You go through here, you come back through here, you can't get back down to here. Now, actually, sometimes you can. I think I talked about this in the pre-calculus class last time. These are all linear functions that we set equal to 0. There are no squares or cubes in here. And as you know, since you've done the homework, it's squares and cubes that cause you to go through the x-intercepts in a nonlinear fashion. By that, I mean, since all these are linear expressions, no squares, you got to go straight through 6, straight through 4. So, you know, you could say, well, I'll come down here and I'll turn around here and then I'll come down here, go through here and come back up. Okay, you can't do that with this function because all these terms are of degree 1, they're linear. Okay, so you got to go through 6, through 4, and then you got to get to this. You can't get to it because you can't go through the x-axis again. So you got to start down here, and you come up here, and you turn around, and you come back down, and then you come on up through 5. Now you know that when x gets big, this thing gets really big. Okay, so for large x, you're going to get really big numbers. So as x becomes large in this direction, your numbers shoot off, they just get steeper and steeper, and you have this kind of behavior. If x gets large in the negative direction, then you're going to have a large negative number, because if x is a negative number, less than -6, all 3 of these are going to be negative. So your graph is always going to be down, and it's going to get down faster and faster. One thing you don't want to do is you don't want to have it kind of tail off like this. You don't want to have it do this sort of thing. That's never going to happen. It's going to keep getting steeper and steeper. Okay, now, a really important characteristic of this is, and I guess I'm going to use it forward here. Okay. This is going to be close to x cubed when the absolute value of x is very large. So let's just say find y equals p of 10 and y equals p of -10. Use your calculators and see if you can calculate those values. Okay, how do we find p of 10? Well, p of x equals x minus 5 times x plus 4 times x plus 6. So what is p of 10? What do we mean by p of 10? We replace x by 10. And that's 10 minus 5 times 10 plus 4 times 10 plus 6. And I think that's 1,040. Little question mark there, I did it in my head. So we have a question. Want to start? Was I recording or was I not recording? Zoom is acting very funkily, so I'm not sure what got recorded. So while you do this calculation, I'll just review everything that I've done so far, just to make sure it's actually there. It's actually fairly straightforward. Okay, so we have this polynomial p of x equals, well, you see it here. We want to plot the x-intercepts and the y-intercepts and sketch the graph. Well, I emphasized, okay, we want to do the x-intercept. And I emphasize you really ought to write all this out for several of these before you start just jumping in and doing it, because if you write it out, you reinforce it and you're more likely to remember it 3 weeks later when you have a test over it, or later on when you need it in another course. It's kind of important to write things out carefully. Okay, so anyhow, if the x-intercept occurs when y equals 0, that has to be second nature. We have to understand why that's so. Okay, well, then we replace y by 0. We get y, or 0 equals all this. And how does 0 equal all this? Well, that's only going to be the case if this is 0, or this is 0, or this is 0. So this splits into 3 equations. This equation, or this equation, or this equation being true makes the whole thing true. Okay, well, we easily solve these equations, and it's trivial. You can spot the zeros just by looking at it. I recommend you write out the equations, because sometimes you're going to have uglier things in here, and you're going to want to write out the equation and know that you write out the equation to solve it. So I'd say write it out like this. In any case, right there you get your x coordinates of your x-intercepts. The y-intercept occurs when x equals 0. So y equals p of 0. What is p of 0? That means you replace x by 0. So you replace these x's by 0, and you end up with -5, 4, and 6, which are multiplied together to give you -120. So your intercepts are -6, 0, -4, 0, 5, 0, 0, -120. We plot those points, and then we plot our curve. Now, all these factors are linear. They're just simple linear functions. So that when we go through any of these zeros, x-intercepts, we go through in what's very close to the point is like a straight line. So if we zeroed in on this point, we would eventually see something that looks just like a straight line. Just the way the Earth has curvature, but you look at the horizon, it looks flat. Okay, so we sketch our graph. We know we have to go up on this side, because when x is a huge positive number, we have 3 huge positive numbers here. We know it goes down on this side, because if x is a negative number, that's going to give us 3 huge negative numbers. Okay. Now, to emphasize a little further what happens in this end and this end, we say, okay, we let y equal this. And so far we hadn't done this expansion, but we're working on that right now. Okay, I'm saying that this is close to y equals x cubed when the absolute value of x is very large. That is, when x is a great big positive number or a great big negative number. Now, I ask that we evaluate the polynomial p when x is 10. That's what it means to write p of 10. It means you write out the polynomial and you replace x by 10 and take what you get. So if we do that for x equals 10, we get 1120. And we notice that this is close to 10 cubed, which is 1,000. Okay. Now, if we do this at -10, we get -360. And that's not so close to the cube of -10. That gives us -1,000. Okay, well, now we want to do p of 100 and p of -100. Because 100 and -100 are a lot further from these zeros then 10 and negative 10. And you'll see how that works out. First thing we want to do, because it's easier to evaluate this now, at least it's easier for me to evaluate it in my head. And I want to show, there's a point I want to make anyway. If we expand this, then we're going to get a polynomial in kind of standard form as opposed to factor form, expanded form. Okay. To multiply all this out, we can only multiply two things at once, so we pick these two. So I'm going to put big parentheses around these two and leave this out here. When I expand these, that's easy. We get x squared plus 10x plus 24. And then we multiply all this by x minus 5, which is going to be x times x squared plus 10x plus 24 minus 5 times x squared plus 10x plus 24. That's going to equal x cubed plus 10x squared plus 24x minus 5x cubed minus 50x minus 120. 120 ran afoul of the edge of that board. We add our squares together, we get x cubed plus 5x squared. Then we got minus 20 or plus 24x, that's a plus, and minus 50, that's minus 26x minus 50x minus 120. Right there is expanded form of our polynomial. Now, if I want to evaluate this when p is 100, first thing I do is I cube 100. Okay, so let's write it out. P of 100 using this form, what do we get? Go ahead and write out evaluation of P of 100. Oh, right away. Okay. Now, using this form, P of 100 is 100 cubed plus 5 times 100 squared minus 26 times 100 minus 120. Okay. And, you know, that step that step needs to be automatic. And you all are having a little bit of trouble with it because apparently you're not totally comfortable with function notation. Now, if I had a problem says evaluate this function and do f of 10 and f of aardvark and all that stuff, you do great. Okay, so you know it, but it's in a slightly different context here, and apparently that's causing a little bit of distraction. Okay, so you kind of want to get over that. Okay, these numbers, those are what you get for x cubed and the x squared and the x and the negative 120 on the end. My question is, well, can you go ahead and add up those numbers? Don't use your calculator, add it up just using the addition algorithm and see what you get. Okay, now there are 4 numbers to add here. It might be a little hard to see it from the back of the room. So I'm gonna write it out here, and it's maybe going to be hard to read, but there have to be 4 numbers here because I had 4 terms here, right? So we would expect to see 4 terms. Now, everybody should have known in 5th grade how to multiply by 100. Every time you multiply by 100, you add 2 zeros on the end. Okay. Well, whether you know that or not, you can multiply it out a long way or whatever. You get 1 followed by 6 zeros. Okay. And you square 100, you get 1 followed by 4 zeros, and you multiply that 5 by 5, and you get 50,000. and then you get 2,600, and then you get negative 120. And if you add these up, well, first write it out in a column and look at what's going to happen. Okay, now that negative 120 is a little bit of a wild card. If you let's say just do the ones you add, you could then subtract 120. It's going to turn out that 120 doesn't make much difference. Now, you want to write it out like this to add them instead of punching it into a calculator, because if you punch it into a calculator, you don't see what's going on with the size of the numbers. When you add these numbers, you're going to get 0 here in this column, you're going to get 0 in this column. And what are you going to get in this column? Show me some fingers. What's this column going to add up to? Can you read the numbers? They're kind of small. Okay, you give you a hint. There's 0, 0, and 6. You actually write it down like this, so you don't have to look at what I'm pointing at. Okay, just write them down in a column like you would do if you're doing 5th grade addition before they put a calculator in your hands and you forget what you're doing. Okay, right there. 1 followed by 6 zeros. And then 5 followed by 4 zeros. And we've got a question. Okay. Now I've messed up. I ignored the negative on the 2,600. So both of these are negative. So we're not going to worry about those just yet. I've got 1,050,000, right? So I've got what? 1,050,000, right? I've got another mess up here. Left off a couple of zeros, 1/10 to the 3rd. Oh, never mind. 10 to the, okay. I swear I got a good night's sleep last night. I was misfiring this morning. Okay. Okay, so my point is now, if somebody came to you and said, I'm going to give you $1,050,000. Okay. But let's say they said this. I'm either going to give you $1,050,000 or I'm going to give you just $1 million. Okay. Would you be particularly worried about which way it came out? How much different is $1,050,000 than $1 million? Well, it's $50,000 difference, and that's a good bit of money. On the other hand, if you got $1 million, $50,000 isn't that much in comparison, right? So $1,050,000 is pretty darn close to $1 million in that sense. Okay. So I said, okay, it's $1,050,000, call it. Oh, tails, and I called heads. Dang, I lost $50,000, but I've got $1 million, so okay, I can live with that. Does that make sense? Now we could talk about the ratio of this number to $1 million. That means we divide this number by $1 million, and we get 1.05, telling us that that's 5% more. Okay, 5% isn't that much. I mean, yeah, in some cases it could be, but compared to $1 million, though, this isn't much different. Okay, now if I subtract the 2,600 and the 120, instead of $1,050,000, Well, that's going to get us down to 1,047,400. A million, yeah, 47,400. 1,047,280. Okay. Well, that's pretty close to this. If you've got $1 million, it's pretty much pocket change. The difference is pretty much pocket change. You're close to $1 million. That is very important. So, okay, tune in. My point is that this is very close to $1 million. Okay, or pretty darn close to $1 million. What's P of negative 100? Well, if we do the arithmetic, we get negative $1 million. Plus 50,000 plus 2,600 minus 120. And that equals $952,480. 9 million. There's a zero in there. I better write that where you can see it. Not right. It's $950,480. Again. Okay, so now, what's the difference between $1 million and 950,000? It's still only about 50,000, right?
I've never just after one. What is it like?
Not much compared to $1 million, still about 5%. Okay, the point now is this is very close to negative $1 million. Of course, that's negative 950,480. So when you get way out here, when you get out to $1 million, this graph is going to be pretty much the same as the x cubed graph. And that's the whole point of this. Summarize the arithmetic for the result. Okay, I'm going to sketch a graph of y equals x cubed. We know what that graph looks like. Okay, it looks like something like this. I'm not doing this graph on a 4 by or an 8 by 4 rectangle or anything like that. I'm going to put $1 million out here. And I'm going to put negative $1 million out here. Sorry. Put 100 out here and negative 100 out here. Down here is negative $1 million. And up here is $1 million. Now the graph of this polynomial, our P of X polynomial, is going to stay very close to the graph of the X cubed. Like the two graphs are going to look something like this. This is going to be real accurate, but something like this. And then very close to the origin, you got a couple of wiggles. It's going to be like that. You can't even really see these wiggles. But what those wiggles are there, if we expand it, those wiggles are the original graph we drew, which looks something like this. So if we zoom in here, we get this behavior that we understand. When we move out, though, fairly quickly, this graph becomes practically identical to the X cubed graph. Now, why is that important? It's important because the X cubed graph goes up very steep here and goes down very steep here. And that's one good explanation of why we get this and this. This is like X cubed and this is going to be like X cubed. I'll say it becomes like X cubed here. And it becomes like X cubed down here. That's something that'd be very good to understand when you have to sketch these graphs. And we have to understand how these functions behave. Now, if we have another function, actually, I wrote one down over here. No idea where it went. Okay, yeah, let's put this up here. Okay, we'll keep what we did in mind. Let's look at this. We want to plot P of X plus 10. Here's our plot of P of X. What's the plot of P of X plus 10 going to be like? I'm going to erase this Q of X here. I was going to put someplace else with this. Let's come back to this. Okay. Give you a hint. We know 4 points on the graph of P of X, and we know what it's shaped like, right? Negative quite a bit further along. Okay, so again, we have the points. negative 60, negative 40, 500, negative 120, same as we have here. Okay, those are on the graph of P of X. We'll do P of X plus 10 in blue. Can you give me the coordinates of one point on the graph of P of X plus 10? Okay, we got a pretty good answer, a real good answer pretty quickly. I said, okay, take the point negative 60. That's on the graph of P of X. What point would be, what corresponding point would be in the graph of P of X plus 10? Well, it's there right out here. Y equals P of X all right, I'm thinking twice too many times. I'll say what we're saying is that the Y values of this have to be 10 greater than this. So whatever P of X is at a value of X, this is going to be 10 more. In other words, if I plug negative 6 into this, I'm going to get 0. You know, we established that a long time ago just because of this, okay? Because of the factored form of P of X. If I plug negative 6 into P of X plus 10, I'm going to get 0 plus 10. So for example, okay. So there we have the main idea, and you really want to understand this statement here because it illustrates why this statement is true. So you really understand this statement. So now you understand that instead of the point negative 60, which is on the graph of P of X, we get the point negative 610. Now 10 isn't very big. I mean, there's 120, so 10 would only be maybe this high. Probably not even that high, but let's just say this, okay? So what we have is the point negative 60 here. On this graph, we have the point negative 610, where blue, I'm using blue to indicate points on the graph of this new function, okay? And it's going to be the same thing. Somebody's already drawn it out. They went a little too high because of the negative 120, but if we make 10 smaller, okay, we're going to have a point 10 units higher than this one. Then we're going to have a point 10 units higher than this one, and a point 10 units higher than this one. Every point is going to go 10 units higher. Okay? So now we can sketch our graph of P of X plus 10. First of all, let's go ahead and sketch a graph representing P of X. And now sketch a graph representing P of X plus 10. It'll look about like this. Uh-oh. Went through the wrong point down here. Fix that in a minute. going to fudge it a little bit. I'll call this negative 120. And now my blue graph is going to go through here. So it's going to come down like this and come up through here. Like so. Okay. So here's a graph of y equals p of x. I'll erase that label. Then we'll put the y in there, and y equals p of x plus 10. Now, we don't have zeros at the same point we did before. And we're going to have a lot of trouble finding those zeros using algebra, because p of x plus 10 is not going to factor as neatly as p of x did. Well, later in the chapter, we'll get some idea of how we might factor p of x plus 10, but we're probably not going to be able to. Still, this illustrates what? This is a vertical shift, isn't it? Okay. Now, as I said, everybody here today is in my section of pre-calculus, and I think every one of you did well on the homework that asked you to graph a variety of functions. So I'm just going to tell you this, since we've only got about 3 minutes left. The x-intercepts are the same as they are for the other functions. Now, we can write out this equation, and the difference we're going to get x equals negative 4 here, x equals negative 6 here. Here, x equals 5 twice. Why? X minus 5 squared equals 0 means x minus 5 times x minus 5 equals 0, which gives us two values, which gives us x minus 5 equals 0 for this one, and x minus 5 equals 0 for this one. You might wonder why we go to that trouble, but there's a very good reason for it. So you want to see this. You want to write this out. Okay? You want to write this out so you'll see it, because I could well ask you a question on an exam that gets to the meaning of this. So this is x equals 5, and this is x equals 5. And look, we've got x equals 5 twice. Okay? Now, the effect that has on the graph is that when x hits this point, it's not going to be going straight through. It's going to be acting like a quadratic function. It's going to have a parabolic graph, and that parabolic graph is just going to be a multiple of the x squared function shifted 5 units to the right. Because x minus 5 squared is the x squared function shifted 5 units to the right. Now, it's going to be multiplied by this times this, and if x equals 5, this is 9, and this is 11. So it's going to be like 99 times x minus 5 squared. This is going to be a lot steeper, but you still understand that graph, assuming you understand the transformations and everything we've been doing. So it's going to have to act like this. 99 times steeper than the x squared graph. But you know, this is 120 here. If I was doing a 4x4 rectangle, it would be 4 units this way, but 4 units this way, and 4 units on this scale would be really small. Okay, this would be a really small flat rectangle. We stretch that by a factor of 99, we might get something that looks like this. Well, let's see how this comes out now. Okay. Oh, and the other thing is, we don't have negative 120. Even worse than I said. Okay. We're not going to have negative 120 here because if x equals 0, we're going to have to square that 5. We're going to have plus 600. I wrote that down kind of carelessly. Then I got over here to start constructing the graph and realized I was stuck. Okay, we got to go through here. Okay, so now the graph has to do this. Yeah, it's a little too sharp here, but there's the idea. Okay. And the other thing is, on a large scale, this graph doesn't act like the x cubed graph. If I expand all this, I'm going to have an x to the 4th out in front, right? We understand that? I multiply this by this, I'm going to get an x squared, right? Then if I multiply by one of these, I'm going to get an x cubed. And if I multiply it by the other one, I'm going to get an x to the 4th. And that's why you learn to expand some of these things. Okay, so what this graph looks like in the long run is just like an x to the 4th graph, which is a lot like an x squared graph, except it's a lot flatter down here. Okay, so it's like an x to the 4th graph, but it's got these little wiggles in the middle. So it actually comes down here and wiggles down below the x-axis and above the x-axis, and then comes back. Okay. Wiggles near the origin, and that's what we're seeing here. And this would be like a scale of, let's say we've got negative 100 here, plus 100 here, and we have 100 million up here. So we're out of time. I'm not going to do that. There's an explanation of why the graph does the stuff that you saw it do when you did the homework.